Have you ever tried to map out a bustling city onto a tiny piece of paper, only to find everything squished together, making it impossible to see distinct neighborhoods? High-dimensional data often faces a similar challenge when we try to visualize it. T-distributed stochastic neighbor embedding, or t-SNE, solves the crowding problem by using a heavy-tailed student's t-distribution in the low-dimensional space where the data is visualized. The crowding problem occurs because in very high-dimensional spaces, points that are quite far apart can end up looking very close when projected into a much lower dimension, like 2 or 3 dimensions. This makes it difficult to discern natural groupings or structures in the data. t-SNE tackles this by first converting the high-dimensional Euclidean distances between data points into conditional probabilities, essentially measuring their similarity. Then, it attempts to reproduce these similarities in a lower dimensional space. The crucial part is using the student's t-distribution for the low-dimensional similarities. Unlike the Gaussian distribution used for high-dimensional similarities, the student's t-distribution has what we call heavy tails. These heavy tails allow for a larger spread of points in the low-dimensional space, meaning that moderately distant points are effectively pushed further apart. This provides much more room to representing dissimilarities accurately. When you are looking at a t-SNE plot, remember that the absolute distances between clusters might not be directly meaningful. Instead, focus on the integrity of the clusters themselves and the local relationships between points within those clusters. The primary goal is to reveal these local structures and groupings that would otherwise be obscured by crowding. An important aspect of t-SNE's effectiveness is the perplexity parameter. This parameter can be thought of as a knob that controls the balance between preserving local and global structure. It roughly corresponds to the number of nearest neighbors considered for each point, influencing how strongly the heavy-tailed distribution repels points. Choosing the right perplexity is key to getting a meaningful visualization without creating artificial clusters or losing important details. Ultimately, t-SNE's innovative use of the heavy-tailed student's t-distribution in its low-dimensional mapping is a powerful mechanism. It helps us overcome the inherent limitations of visualizing complex data, making previously hidden patterns and clusters clearer and more interpretable for researchers and analysts alike.